Okay, hello and welcome back. In this video, we're going to cover section 12.4 on a process called mathematical induction. So this will be a way that you will be able to prove that some statement is true for all of the natural numbers. Those are the numbers starting from 1 and increasing to every whole number up through infinity, so from 1 onward. So let's start by considering this claim that the sum of the first n odd numbers is equal to n squared. So we can write this out as like 1 plus 3 plus 5. This would continue until our general term, which we could call 2n minus 1. So the claim is that if we sum the first n odd numbers, like this would be the first one, second one, third one, this would be our nth odd number, that this will be equal to n squared. So how can we show that this is true, and especially true for any natural number that we could possibly sum up to, or that we could plug into this pattern? Well, we could start by trying a few samples, like we can say, well, when n equals 1, well, that would just be 1, and that's equal to 1 squared. That one's simple enough. When n equals 2, that's the sum of the first two odd numbers, so 1 plus 3 is 4, which is 2 squared. When n equals 3, that's 1 plus 3 plus 5, which is equal to 9, which is, in fact, 3 squared. When n equals 4, that would be 1 plus 3 plus 5 plus 7, which is equal to 16, which is 4 squared. So the pattern seems to be true. But we've only looked at 4 examples. You can imagine there's an infinite number of inputs we can plug in. So how do we know that this is true in general? And that's where we can use mathematical induction. So first let's describe what it is, and we'll go through a few examples. So let's read the text description, and then I have my own sort of variation of the steps. So it says, suppose that the following two conditions are satisfied with regard to a statement about the natural numbers. Condition 1 is that the statement is true for the natural number 1. So we know that it's true for like the first possible input that we can plug in. Condition 2 says, if the statement is true for some natural number k, meaning we'll assume that the statement is true for some general term k, when n equals k, and it can be shown to be true for the next natural number k plus 1. If both of these things are true, then the statement is true for all natural numbers. So I think let's look at an example first, and we'll come back to this to try to like reinterpret what this is saying. And this is sort of my own version in terms of the steps that we'll do. So we're going to first show that the statement is true for n equals 1. Then we're going to assume that it's true for some general term k, and show that if that general term is true, the general next term is true when n equals k plus 1. And if all of these things are true, then we will have proved that the statement is true for all natural numbers. So let's start at the example we were just looking at. This is the sum of the first n odd numbers. So first let's start, and we did this already, but we'll follow the process. Let's start by showing that the statement is true for n equals 1. So we have 1, which is equal to 1 squared. The statement is true. This feels kind of redundant, but this is actually a pretty important step, and um, we'll see in a second. So the second step is to assume that this is true for n equals k. So we're saying that k would be some term, maybe somewhere in the middle. There's some general term. And by saying this, what I mean is we'll plug in k for n, 1 plus 3 plus 5 plus, pattern continues until we get to 2k plus 1. I'm sorry, 2k minus 1. And we're going to assume that this is equal to k squared. So we're just plugging in k for n, and we'll say we will assume that this is true. So our third step now is to show that if it's true for n equals k, the statement is true for n equals k plus 1. So I'll say, so show true for n equals k plus 1, meaning 1 more than k. That's the next term in terms of the natural numbers. So what we'll do is expand the pattern on the left until we get to k plus 1. So we would have 1 plus 3 plus 5. We're going to pass the k term, which is 2k minus 1. And then the last term where we will stop is when we're at 2 times k plus 1 minus 1. So this was the first term, the second term, the third term. This is the kth term. And then this is the next, just the general next one, k plus 1. So we're plugging in k plus 1 where there was an n originally. And what we're trying to see is this going to equal what we would expect to see on the right side for k plus 1, meaning is this going to equal k plus 1 squared? And I'll put a question mark here. That's what we need to show. We need to show the left-hand side can be turned into the right side. So the trick here is to use what we said in part 2, where we assumed that it was true for k, meaning if we are assuming that this is true, then this whole first part, up until the k term, should just be equal to k squared. So I'm going to replace that with k squared. And then we have our k plus 1 term. So I'll write that here. So 2 times k plus 1 minus 1. And now let's see if this will be equal to k plus 1 squared. So let's distribute the 2. So this will give us k squared plus 2k plus 2 minus 1. So that's k squared plus 2k plus 1, which if we factor this, factors of 1 that add up to 2 are 1 and 1. So this can be k plus 1 times k plus 1, or k plus 1 squared, meaning the sum of the first k plus 1 terms is equal to k plus 1 squared. So what we've done here is actually prove that it's true for all natural numbers. And I'll draw out a little diagram to help visualize. So I'm drawing some little boxes. So let's say this is the box for n equals 1. And this is for n equals 2. This would be where n equals 3. And this can continue. And let's imagine this is where n equals k. And then the next one is k plus 1. And then this continues onward. So I'll fill these in to show that we've shown that it's true. So in step 1 of the induction process, we plug in 1 for n and just show that the original statement is true. So we know for sure that it works for n equals 1. Then we assume that it's true for some general statement k. So I won't totally fill that in because we're doing some assumption. But what we showed in part 3 is that if we assume the previous term is true, then mathematically it works out that the next term, if we go to k plus 1, is also true. We ended up with k plus 1 squared. So that means, assuming that k is true, we've shown that k plus 1 is true. So it kind of like turns on the next unit in a way, if this is like a string of lights. So how does this prove that it's true for all natural numbers? Well, if we believe that if the previous term is true, the next term is true, based off of our work in step 3, then we can go back and say let k equal positive 1, since we do know for sure that it's true for 1. And we showed in general in part 3 that if it's true for one term, it will be true for the next one. 2 would be our k plus 1. It's like 1 plus 1. Well, since it's true for 2, then it's going to be true for 3. And so this continues. It almost like lights up all of these little boxes, and it just continues up through infinity. So from 1 to infinity in the natural numbers, since we know it's true for the first term, and if it's true for one term, it's true for the next term, it's going to be true for all of these next terms. So we can say, I'll add like a conclusion statement here. Therefore, 1 plus 2 plus, I'm sorry, not 2, but 1 plus 3 plus 5 all the way up to 2n minus 1. The sum of the first n odd integers will be equal to n squared. And I'll say for all n as a natural number. This doesn't prove for all real numbers, but at least for all the natural numbers, we can know that it's true. So let's go back and look at their description, just to read through again. So it banks on two conditions. The first condition is that the statement is true for 1. So we kind of set our initial condition. Then we say, if the statement is true for some number k, it can be shown that it's true for the next natural number k plus 1. So those are the two pieces that we need for a proof by induction. So it's often visualized as falling dominoes, where if you know, based on condition 2, that essentially if one domino falls, it's going to always make the next domino fall, then by showing that the first term is true, we're essentially like knocking over that first domino. And then condition 2 says that it's just going to continuously knock over every next domino. So it's a way that we can prove something is true for every natural number. So let's go through a few more examples. We'll see some slightly different kinds of questions, but the general process will be the same. We'll follow these 3 steps. So example 2 is a little bit different. They tell us that, or this is the claim, that 2 to the power n is greater than n for all natural numbers. So let's go through those 3 steps. We can first say, first we want to show it's true for n equals 1. So that would be 2 to the first power, which is 2, is definitely greater than 1. So that's true. So we know for sure we can essentially knock over that first domino. But we need to show that if some general term is true, the next term will always be true. This gets a little bit tricky. But first, let's assume, I'll say part 2, let us, maybe I'll stick it over here. Let's just assume that this will be true for n equals k, meaning we'll assume that 2 to the power k is greater than k. So now with that assumption, let's look at when we need to show that this is true for n equals k plus 1. So what we want to try to say is that 2 to the power k plus 1 is going to be greater than k plus 1. So right now we're questioning if this is true or not. Let's think about how we can do this. 2 to the power k plus 1. We typically want to try to use the statement from part 2, that, that thing that we assume to be true. So we need to try to express 2 to the power k plus 1 somehow with 2 to the power k. Well, if you notice, we can re-express this as 2 times 2 to the k. If we were to multiply these out, it would add another to the exponent. Like if we did x times x cubed, that would give us x to the 4th power. And so if we are assuming that it's true for k, and we have produced 2 times 2 to the k, well, we can essentially multiply both sides of this inequality by 2. We should be able to say that this is greater than 2 times k. And then 2 times k we can write as k plus k, which we can argue is going to be greater than k plus 1, assuming that k is greater than 1. If k was equal to 1, they would be equal to each other, but since we're focusing on every term after 1, this will always be true. 2 plus 2 is greater than 3, and so on. So since, and this is 2 to the power k plus 1, we rewrote it as 2 times 2 to the power k. Since it's greater than 2k, which we're saying is also greater than k plus 1, well then we can just say that 2 to the power k plus 1 is greater than k plus 1. That's what we wanted to say from the beginning of part 3. So we started by showing that it's true for n equals 1. We assume that it's true for n equals k. Then show that it's true for n equals k plus 1. So we can say 2 to the n will be greater than n for all n from the natural numbers. So let's look at a couple more. In example 3, we see a statement that we've seen from a previous section when we were looking at sequences and series, that the sum of the first n terms is equal to n times n plus 1 over 2. So let's go through that process again. First, let's look at when n equals 1. On the left side, we would just have 1, and this should be equal to 1 times 1 plus 1 over 2. Well, that looks like 1 times 2 over 2, which equals positive 1. So it's true in our first case. Now let's assume it's true when n equals k. So 1 plus 2 plus 3 up to k is equal to k times k plus 1 over 2. Now let's try to show that it's true when n equals k plus 1. Meaning we'll sum all the way up to k plus 1. So 1 plus 2 plus 3. We're going to pass k and go to the next term, k plus 1. And we need to show that this will be equal to the right side of our original formula if we were to plug in k plus 1 for n, meaning this needs to be equal to k plus 1 times k plus 1 plus 1 all over 2. So on the left side, in part 2, since we assumed 1, the sum of 1 up to k is equal to k times k plus 1 over 2, we can replace up to k with k times k plus 1 over 2. And then we still have the next term added, so plus k plus 1. Now let's see if we can turn this into the right side. So it looks like we want to be all over a denominator of 2. So let's get a common denominator. This would be k times k plus 1 over 2. For the second term, I can multiply the top and bottom by 2. And so let's combine this into a single fraction, and I'll distribute these two terms. So on the left side, I'll get k squared plus k. And on the right side, I'll get plus 2k plus 2 all over 2. So this will give us k squared plus 3k plus 2 over 2. Which when we factor this, factors of 2 that add up to 3 are 2 and 1. So I can write it as k plus 1 times k plus 2 over 2. Which that k plus 2, we have the k plus 1 on the left side. K plus 2 we can write as k plus 1 plus 1. We can just split the 2 into two ones. We'll have k plus 1 times k plus 1 plus 1 all over 2, which is our right-hand side here. So we showed it's true for the first term, and if it's true for some general term, it will be true for the next one. So that means it will be true for all natural numbers. So I can say, therefore, the sum of the first n natural numbers equals n times n plus 1 over 2 for all natural numbers. All right, let's look at one more example about divisibility, so we can also prove these kind of statements as well. We want to show that 3 to the power n minus 1 is divisible by 2 for all natural numbers. So let's start when n equals 1. This will be 3 to the first power minus 1, or 3 minus 1, which is equal to 2, which is divisible by 2, so it's true. So now let's assume that it's true when n equals k. So we'll assume that 3 to the power k minus 1 is divisible by 2. So now let's look at when n equals k plus 1. This one's a little bit tricky. So we'll have 3 to the power k plus 1 minus 1. So it would take some time playing around with this, but the trick is to, if we add and subtract, so let's subtract 3 to the power k and add 3 to the power k, and then we still have the minus 1. This seems a bit weird, but we haven't changed anything because we added and subtracted the same term. Well, now on the first two terms, they both have 3 to the power k in common. Like we can, and it might be helpful to write out the first term as 3 times 3 to the power k. Let's imagine if we factor out 3 to the power k out of the first two terms, we would get 3 minus 1 left over. And then we have plus 3 to the power k minus 1. So in part 2, we assumed that this second part, 3 to the power k minus 1, is divisible by 2. And then notice if we simplify the parentheses for the first term, we get 3 to the power k times 2. So since we know the second term is assumed to be divisible by 2, our other term is multiplied by 2, so it will definitely be divisible by 2. So that gives us a true statement. So it's true for the first term and the general next term. So we can say 3 to the power k minus 1 is divisible by 2 for all natural numbers. So it's worth playing around with these and going through a bunch of examples just to start to try to get a feel and a sense of how this proves the statement for 1, 2, 3, 4, 5, all the way up through infinity. Again, I view it as this kind of chain reaction where we know the first term is true. We know that if some general term is true, the next term is true. So then we can start back at the first term and say the next term is true, then the next term is true, the next term is true, and so on. All right, that'll be it for this section. So playing around with mathematical induction, so we can start to prove some of the statements that we've taken for granted before, maybe some of our previous claims. All right, that will be it for this video, and I'll see you next time.